Why is it that gold stays shiny for thousands of years, while iron seems desperate to return to the earth as a pile of red dust? The answer lies in a simple yet powerful map called the Ellingham diagram. It's essentially a cheat sheet for the entire field of metallurgy, telling us exactly how much energy rent a metal has to pay to stay pure, and what happens when we turn up the heat. To understand it, let's look at a blank graph. On the horizontal axis, we have temperature. On the vertical axis, we have something called Gibbs free energy, or delta G. For our purposes, just think of delta G as a stability score. The lower a point is on this graph, the more stable that substance is. If a metal oxide is at the very bottom, it's incredibly happy to stay an oxide. If it's at the top, it's barely holding on to its oxygen at all. Let's plot our first line. Let's say for silver. Notice how the line starts near the top and slants upwards as we move to the right. This upward slope is actually a beautiful piece of physics. When a metal reacts with oxygen gas to become a solid oxide, the system becomes more ordered. In thermodynamics, we say entropy decreases. Because of how the math works out, this causes the line to climb as temperature increases. Now, let's add more lines. Let's look at aluminum way down at the bottom and iron somewhere in the middle. Here is the first big aha moment. Any metal whose line is lower on the graph has a stronger hunger for oxygen than the metals above it. This leads us to a visual rule of thumb: a metal can steal oxygen from any oxide whose line sits above it. Since aluminum's line is much lower than iron's, if we mix aluminum powder with iron rust and ignite it, the aluminum will aggressively rip the oxygen away from the iron. This is exactly how a thermite reaction works. But wait, if most lines go up, how do we ever get pure metal back from these stable oxides? This is where the real hero of the Industrial Revolution enters the frame: carbon. Watch what happens when we plot the line for carbon reacting to form carbon monoxide. Unlike the metals, this line slants downwards. As it gets hotter, carbon becomes more and more hungry for oxygen. Notice this intersection point right here. To the left of this point, the metal's line is lower, meaning the metal keeps its oxygen. But once we cross that temperature threshold, carbon's line dives below the metal's line. Suddenly, carbon is the more stable partner for oxygen. It snatches the oxygen away, leaving behind pure liquid metal. This intersection is why we didn't have an Iron Age until we built furnaces hot enough to reach that crossover point. The Ellingham diagram isn't just a collection of random lines, it's a competitive landscape. It tells us that everything in the universe is essentially in a massive tug-of-war for oxygen, and the winner is simply whoever can stay at the lowest energy level at a given temperature. It's a map that turned the magic of blacksmithing into the precise science of the modern world.